G'day Year 12 Method students. In this video we're going to be looking at how to find the area between two curves. So let's have a look at the theory behind it, and then we'll do, as always, a few examples to try to get the hang of how this works. So if we look at this sort of picture that we've got on the page here, and imagine that we were trying to find the area that is contained between this function f of x and this function g of x. Well, this kind of shaded area here between x equals a and x equals b can actually be found by using the area under a curve, so the area between the curve and the x-axis, and a little bit of subtraction. So let's just start by thinking, well, if we found the area between the function f of x and the x-axis, well, really that area is sort of this part that I'm shading here in pink. Right, so that area would equal the integral from a to b of the function f of x. Right, but if what we're interested in is not the area between f of x and the x-axis, it's actually the area between those two functions, well then what we would want to subtract is this area here. We would want this area to kind of be subtracted from that, and that area would actually be the area under the curve g of x, or the area between g of x and the x-axis. So that area would be the integral from a to b of the function g of x. And so you can see from that quick sort of visual that if we were to take the pink area, the area under f of x, and subtract the orange area, which is the area under g of x, then what we'd be left with is the area that we actually want, and that is the area between the functions f of x and g of x. Okay, and hence we get this formula here that says the area would equal the integral of, or the integral from a to b of f of x minus the integral from a to b of g of x, which we know from our integral sort of rules, our rules for definite integrals, that we can actually write this as one single integral, and that is the integral from a to b of f of x minus g of x. So this formula here is essentially how we find the area between two curves. A really key thing that we have to get right is that the function that goes first in this subtraction is always the function that is has the higher y values. It's the function that's on top when you look at its graph, and the function that we're subtracting is the one that's on the bottom. If, and there's a little note here, if the graphs intersect between a and b, then we'd actually need to separate the areas into sections, because if they intersect, that would change which function's on top and which function's on the bottom. Okay, and we'll do an example where we have to deal with that a little bit later on. Let's get into the first one. Example 1, we're going to find the area of the region bounded between the parabola y equals x squared and the line y equals 2x. So you can see we've got the graph here, and we should know from our knowledge of functions that this one's the parabola, y equals x squared, and the linear graph is y equals 2x. Okay, so you can label them there. Now, if we're going to find this shaded area, what we first need to know is where do the two graphs actually intersect. Okay, so where do these points of intersection occur? Because that will give us our lower and upper terminals when we're setting up our integral. So let's find the intersection first by letting x squared equal 2x. Okay, so let's let x squared equal 2x. Now we can solve that by getting both terms to the left-hand side, taking out a common factor, which is x. And from that we get they intersect when x equals 0 and x equals 2. So we can sort of tell from the graph that they would intersect at the origin when x equals 0, but they also intersect over here when x equals 2. So this shaded area is going to be given by the integral from 0 to 2 of, now remember it's the function that's on top minus the function that's on the bottom. So in this case the function that's on top in the region that we're looking for is the linear function 2x. The function that's on the bottom is x squared. And so now our job to find that integral is to evaluate that, to find the area is to evaluate the definite integral. So, and to differentiate, 2x, when we add 1 to the power and divide by the new power, becomes 2x squared over 2. So that'll actually cancel to just x squared. And the antiderivative of x squared is x cubed divided by 3. Right, and now we sub in our terminals and solve for the area. So we've got 2 squared minus 2 cubed over 3. Minus, when we sub in 0, both parts of the antiderivative become 0. So our area is simply 2 squared, which is 4, minus 2 cubed on 3, so 8 on 3. And we know the number 4 is really 12 over 3, so we can think of it this way, and ultimately work out that the area is 4 on 3 units squared. All right, let's have a look at another example. We're going to find the area between two curves. In fact, you might want to, now that we've just done one, you might want to pause this and have a go at the example yourself and then play the video and see if you've got the same answer as me. But but let's get stuck into it. So here we've got calculate the area of the region enclosed between the curves y equals x squared plus 1 and y equals 4 minus x squared. So these are both parabolas, but again, just to label the graph so we can easily identify which one's on top, which one's on the bottom. The positive parabola is x squared plus 1, so y equals x squared plus 1. And the negative parabola is y equals 4 minus x squared. And the question told us that the lines that are shown are x equals 1 and x equals negative 1. So essentially this line here is negative 1, and that's 1. And so we can set up the integral to say that the area will equal the integral from negative 1 to 1. The function that's on top in this region is 4 minus x squared minus the function on the bottom, which is x squared plus 1. Okay. If we work it out that way, we'll get the right answer, no problem. There is a little bit of a shortcut that I just want to point out, or an alternative method that can be a little bit easier. Because these functions are both symmetric around the y-axis, and the interval from negative 1 to 1 is also symmetric around the y-axis, we could actually find just the area on the right-hand side and then double it, because this area on the right-hand side is going to be equal to the area that's on the left-hand side. And that would be slightly easier because it would then let us use terminals of 0 and 1, which are a bit easier to sub in than using negative 1. So I'm actually going to say that let's say, let's call this area area 1. I'm going to say, well, area 1 equals 0 to 1, the integral, sorry, from 0 to 1 of 4 minus x squared minus x squared plus 1 with respect to x. And that's equal to, well, before we integrate, actually, let's simplify. So 4 minus 1 is going to give a 3, negative x squared minus x squared. So we're going to have minus 2x squared with respect to x. So simplifying first. And now if we evaluate this definite integral, well, 3 integrates to 3x, and the minus 2x squared becomes minus 2x cubed over 3. Okay, so we can now sub in x equals 1. That gives us 3 minus 2 times 1 cubed, so just 2 times 1 over 3. Minus, and subbing in 0 gives us, well, first and second terms both become 0, so 0 minus 0 in that second bracket. So really we're just working out 3, well, it's 3, but let's call it 9 on 3 minus 2 on 3, which equals 7 on 3 units squared. Now remember, using this method, we were just evaluating the right-hand side of the area. The total area that we actually want, which includes this part, is going to be 2 times the answer that we came up with. So the total area equals 2 times 7 on 3, which is 14 on 3 units squared. Okay. Looking back to what we could have done at the beginning, had we evaluated this integral, we'd get exactly the same answer, just might have been slightly trickier because we had to sub in a terminal of negative 1. So it's worth knowing that there are alternative methods anytime you've got equal areas in different parts of a graph.